Hi, this is Ling Hee. Welcome to Ling Hee Math World. In my previous video, I've proved E is irrational number by proof by contradiction. This video is using similar approach to prove pi is irrational number through the HKAL Pure Math 1978, paper 2, question 8. So here is the question. I'll give you a brief idea of my proof, and then I'll explain part by part. So the brief idea is proof by contradiction. We assume that pi is rational, and then we construct a small interval, while the middle part here will be an integer. And this interval is small enough that integer should not exist. So that draws a contradiction. So this is similar to the proof for E is irrational number in my previous video. Okay, so as an overview, we construct a function f and x like this. So this function looks like complicated, but for clear look, this is a polynomial of power 2n. And this polynomial, we can construct inequalities in part A1 and A2. The key is of course part A2, because we apply this inequality to draw out contradiction. And then part B, the main purpose is to set this part to be an integer. Okay, so all these parts here, I try to set this middle part be an integer. And then this part, I try to make it small enough by the limit. In the original question, they do not require you to prove A, B, and this limit. But in my video, I'll explain how to prove this as a completion. Let's start. So main aim is prove pi is irrational number. So by contradiction, assume it's rational, we construct a small interval that consists of an integer. So part A, that we have this polynomial f and x, and I try to construct this inequality. So if x is in between 0 and a over b, then prove this. That just means that f and x has the maximum, this number. Alright, so this is not hard to prove. This is we consider this function. So we consider this function, which is a quadratic function. This function has zeros at x equals 0 and x equals a over b. Okay, by direct substitution, basic algebra, you can check that. And then by symmetry, or you can use differentiation, use completing square, wherever, you can find that the maximum occurs at x equals a over 2b, and the maximum value is this one. By just direct substitute this x equals to a over 2b back to the quadratic function, we have this. And for the graphical explanation is this, and 0 and a over b are the zeros, while this one, the midpoint is the maximum occurs. Therefore, the function f and x, which is constructed by the quadratic function to the power n divided by n factorial, which is a constant in the closed interval 0 to a over b, is just this one, and the maximum is the same as the original quadratic function by substitute x be a over 2b. So this part, maximize it, it is a squared over 4b. That's why I have this result. Okay, so I try to maximize it. And by the quadratic function, that this is above 0, so the function is greater than or equal 0 in the closed interval, or I should say the minima occurs at the endpoint, that is fn 0 and fn a over b, which are 0, then it is greater than or equal 0, and as for the open interval, it is always greater than 0. That's the result of part A1. Then let's move on to part A2, where I try to show that if pi is less than or equals to a over b, we have this inequality. Of course, this inequality is based on the fn multiplied sine x, and then we integrate it in the middle part. Therefore, we can just apply the properties of the part A1, and we can do the job very easy. So let's see. So pi is less than or equals to a over b. Then integrate this one. We try to maximize this part and this part. So fn x by part A1, maximize it, is this constant. Now note that this is a constant. And for sine x in between 0 and pi, this is in between 0 and 1, and maximize it is 1. Okay, by direct integrate this, note that this is not complicated as this is a constant. So integrate this one, you get this. Okay. So the right hand side of the inequality has been proved, while the left hand side is not hard, but you need to be a little bit more careful. So I try to prove the left hand side now. So the function y equals fn x sine x is continuous function, while this function is greater than 0 in the open interval 0 to a over b. That's why when we integrate this function, must be greater than 0. It cannot be equal 0. So it cannot be equal 0. It must be a strict inequality greater than 0. Here I emphasize it is continuous because if the continuous condition is not, then may be equal 0. Okay, so the continuous condition is strong, more than enough for the integral that not equal zeros. On the other hand, if it is not continuous, you may consider the Dirichlet function, which is fx equals 1 for rational number and 0 for irrational number. So this function is fx is greater than or equals 0, and for at some points fx is greater than 0. However, when you integrate this, it is equals 0, and you can check it by the Lieberg integration. We will not go into details in this video. I will make another video about Lieberg integration in future. What I want to emphasize is the condition continuous gave the function so that just means something like that. So this is some function gx, which is continuous, and it is greater than or equal 0. Then we can surely construct a small range epsilon 1, epsilon 2, where this area is greater than 0. Okay, so this is can be applied for continuous. If it is discontinuous, it is much complicated. Then we will discuss it in the Lieberg integration. Okay, so the inequality is proved. Let's move on to part B. Part B, the original question is simpler. They just ask you to use condition A and condition B and construct this part. Well, this part is an integer if pi is a over b. For me, I will prove part A and part B for you. So part A, we define the fn x with this function. So this function is certain derivative of is the sum and difference of certain derivatives of fn x. So this is not hard to prove, but it is a little bit tedious. If you find it is too tedious, you can skip this part. Basically, we apply the Leibniz formula. We observe the function fn is a degree 2n polynomial, and fn0 kth derivative is the same as fn a over b kth derivative also equals 0. This can be checked by direct substitution because these two terms are not absent, and for the nth derivative of x to the power n is n factorial. Okay, similar to this one, a minus b x to the power n derivative is negative b to the power n factorial. Okay, so these two are also 0 if k is greater than n. Okay, because we differentiate a constant, it is 0. Alright, so this part is by the Leibniz formula. We differentiate this one. We already checked that if k less than n, the derivative of putting x be 0 and a over b are all 0. Therefore, we only need to check for k greater than n, which is by the Leibniz formula we have these. That just means for some terms it is because the derivative is too large, then it will vanish. So it starts from this term and end up with this term. With the middle term, I do not write it because this term consists of the factors x multiply x a minus bx. So these are the terms consist of factors x multiply a minus bx. So this is what you need to know. Okay, we do not need to write them explicitly. Now we can substitute x be 0 into this expression. We can find that this part is 0. This part, of course, must be 0. And this part, you substitute x be 0. This become a to the power, this become the derivative of this part, and then you substitute x be 0. This part is an integer, and n factorial and n factorial cancel out. As a summary, this part do not have any fraction. This part is an integer. Similarly, I put a over b into this expression. This part is the same as above. This is 0. This part is 0. And as for this part, the n factorial and n factorial cancel. That means no fraction. And then this part, you substitute x be a over b. Note that this the power of this one is less than the power of this one. That's why the fractional part will also be cancelled. That means this is also an integer. So by these tedious calculation, we find that fn0 and fn over b are both integers. Now, let's move on to part B. Part B asks you to show that the derivative of this thing is fn x sine x. This is not hard to prove. By this definition, we just differentiate twice. Look at this part. If we differentiate, look at this part. This one is a degree 2n polynomial. So this part, if we differentiate once more, it is 0. That's why I have the second derivative of fnx. I have this part is 0, and this part is just fnx minus fnx. Now, we know the second derivative in terms of fnx and fnx. The derivative of this expression, which is the answer proof in the left hand side, is by the product rule, which is this one, while these two terms vanish. And this one, I just apply what I just said. So I substitute this part into here. I cancel the fnx with this one. I have fnx sine x. B gives an integral explanation of part B1. So we just use the fundamental theorem of calculus, integrate this one is the result of this one. Therefore, this is the part B1 by B, and by fundamental theorem of calculus, I have this, integrate this one is this part, substitute lower limit and the upper limit. Note that we have this result: sine 0 equals sine pi equals 0, sine 0 is 1, cosine 0 is 1, cosine pi is negative 1. Therefore, it's just use all the substitution, we get this. Okay, last part B2 is the main purpose of this question. We want to prove pi is never a rational number. But first of all, we need to prove this part, limit of this one. This limit is 0. The original question do not require you to prove, but let me prove it here. And this is not hard. The idea is we break this into two parts. While the first part is the finite terms, which of course is a constant, while the second half is small enough, that means it can be tends to 0. By the Archimedean property, for all x belongs to positive real numbers, the existence n, actually this is not necessary to be positive, okay? But as for simplicity, we just check for positive. There exists a natural number n such that n is greater than x. By the Archimedean property, we can take an m belongs to a natural number such that m is greater than absolute alpha. Therefore, I can break this into two parts. For large enough n, large enough that means n is greater than m. We consider this expression n to the power alpha to the power n over n factorial absolute is alpha over 1 plus absolute alpha over 2 plus until this part. Okay, here this is the first part, becomes this one, which is a constant because m is fixed. For every alpha, we can define an m. This is fixed, so alpha, m are both fixed. That's why this is a constant. So a constant multiply this part. So this part, I try to make every denominator to be m. So this is less than or equals, denominator becomes m. The power is n minus m plus 1. This fraction, note that this is in between 0 and 1. So if we take limit of this part, when n tends to infinity, it must be 0. Therefore, by implying the Sandwich theorem, we have 0 is less than or equals this limit, which is less than or equals this expression, while this is a constant, multiply this part, which is tends to 0, constant multiply something tends to 0, 0. By Sandwich theorem, this limit is 0. Now, here comes the most interesting part of this video. Now we try to prove pi is irrational number. So on the contrary, we prove by contradiction. On the contrary, we assume pi is rational number. That means pi equals a over b. A, b are positive integers. B is non-zero. The GCD of a and b is 1. Then construct the 2nth polynomial f and x as above. By part A2, we can apply because pi is less than or equals a over b. Then we have this inequality, which is the result of part A2. By B1, this part is this part, and by our assumption pi is a rational number, pi equals a over b. However, pi equals a over b, this part is an integer by a. So we can let k equals this part, and this part is an integer, and we let it to be k. And then by the lemma, this part tends to 0. That means this part tends to 0. That means there exists an n log belongs to a natural number such that this part is less than 1 for n greater than or equals n naught. So if you feel some confusion, just you need to know this part can be small enough. Okay, just say for some n, this part could be 0.5. Therefore, I have 0 by this inequality. I have 0 less than an integer less than 1. Now that's a problem. In between 0 and 1, is there an integer? From the inequality here, it suggests that there is an integer in between the small interval, the open interval 0 and 1, that draws a contradiction, which proves pi cannot be rational number. That means pi is irrational number. Okay, so I hope you enjoyed this video, and after this video, I find that those who take A-level pure math in the 70s are crazy guys. Okay, I used 2 hours to finish this proof. I don't know how they can finish this whole exam with 9 questions in 3 hours. Okay, this is mysterious. Okay, so thanks for watching.